what I always say. I don't think I always say that. I don't know what I'm talking about. Okay, so transfer functions. So in lecture 3.7, we briefly introduced the transfer function, a very important dynamic system representation to which we now turn our attention. So we're going to revisit it now, and we're going to talk about it for the next several weeks. And actually, we're focused on it the next several weeks. We're going to, in chapter 9, become a little bit more familiar with the transfer function. And then in chapter 10, we're going to learn this impedance-based modeling, which is a technique that allows us to go directly to a transfer function from the linear graph model, which is nice. We don't have to go through state space models, which has a slight advantage to it. It's honestly not that different, but there are a couple nice little tricks. Do you guys remember when we used impedance methods in the mechatronics course to do circuit analysis? Those were the days, man, right? And so it's gonna look a lot like that, but it's gonna be with transfer functions, and there will be things like an across variable divider rule and a through variable divider rule. So sort of like the voltage divider, etc. So like, and then there are those nice shortcuts that you can do, Norton and Thevenin equivalent sources, etc. So we're going to revisit that in this general form for transfer functions, and for generalized systems of a bunch of different varieties, not just for electronics. So it's pretty cool. I like it. It's chapter 10, so we're going to be spending like next week doing that. And but the main object, the main way that we'll be representing systems will be the transfer function. And then we're going to do frequency domain stuff, which mostly centers around the transfer function again. And then we're going to switch gears. We'll have a midterm, and then we're going to switch gears, and we're going to do the last like 5 weeks, 4 weeks maybe, because the class got all screwed up. But 4 or 5 weeks on control theory and control systems. And the main object we'll use to represent systems in that section will also be transfer functions. So you can think about this as like this point at which we're kind of transitioning to mostly using transfer functions to describe our system models. It's not exclusive. We'll still use some of the other modeling techniques, but it is, I would say, the focus of the course is the different things that you can do with transfer functions, not just the objects themselves. But the main way that we'll represent these systems going forward will be with transfer functions. So important, not like last time we brought them up for like 30 seconds. We were like, hey, transfer functions, and then they disappeared for like a couple months. So cool. So we're going to repeat the definition of the transfer function because it's been a minute. So we'll do that. So let a system have an input u and output y. Let the Laplace transform of each be denoted capital U, capital Y, both functions of complex Laplace transform variable S. A transfer function h is defined as the ratio of the Laplace transform of the output over the input. So this is how we define the transfer function. We start out, like in the dynamic systems section, we'll mostly use h as the transfer function symbol. But to be honest, once we get to controls, we're going to start doing lots of transfer functions in the same problem, and there'll be like lots of different symbols. We'll run out of symbols, so it'll be like H and then G and then A, and then you're like, oh crap, now we're off in like conflicting symbols land. So it's great. As usual, never enough symbols. The transfer function is exceedingly useful in many types of analysis. One of its most powerful aspects is that it gives us access to thinking about aspects and access sound really similar. Thinking about systems as operating on an input and yielding an output, So like input comes in, transfer function operates on it, and it yields an output, y. So like that's the way that we can think about transfer functions. And by extension, because we know we can represent a system in a transfer function form and equivalently in an input-output differential equation form and equivalently in a state space form, all of these systems we can think of as operating on inputs and yielding outputs accordingly. So, yeah. Great. So we'll be doing lots of good stuff with these transfer functions. As we learned in Lecture 3.7, one can easily convert a state space model to a matrix transfer function model with the formula 9.2. So we use this. This is what we use to go from our state space model to a transfer function model, and then by essentially relating a transfer function to an input-output ODE is quite easy to do by inspection. You just go through the argument once and you can do it by inspection. So this is the key formula that takes us from a state space model to a transfer function model. And right now, that's the only way we know how to get a transfer function. Either that, or if you have an input-output ODE. So we're dependent on this. In Chapter 10, we're going to learn how to derive transfer functions directly, though. So cool. You can also use the definition. So if you have an input-output ODE, you take the Laplace transform of it, you can solve for this directly as well. Any questions on transfer functions? Awesome. I need a cool catchphrase like awesome possum. Yeah, you guys like it? I should also do this. Finger gun, just one finger gun. Awesome possum. You guys like it? I'm going to work on it. I'll get back to you.